In the previous subtopic, we have learned about the macroscopic quantities, which is pressure, temperature, and volume. Now, we're going to focus on microscopic quantities, which relates to the motion of the atoms or molecules. Why we need kinetic theory of gases? This is because it relates the macroscopic property of gases to the microscopic property, which is the motion of atom or molecules. Here is the assumption of kinetic theory of gases. The first one, all gases are made up of identical atoms or molecules. The second one, all atoms or molecules are inconstant, move randomly, collide each other with the walls of the container. All collisions are perfectly elastic collision, and the volume of the atoms or molecule is negligible when compared with the volume occupied by the gas. Intermolecular forces are negligible except during the collision, means there are no interaction, attraction, or repulsion between atoms or molecules. The duration of collision is negligible compared with the time spent traveling between the collision. According to the kinetic theory of gases, all gas molecules are in a state of constant random motion. Individual particles move at a different speed, constantly collide and changing direction. We use velocity to describe the movement of the gas molecules, and we consider both speed and direction. Gas molecules moving in opposite direction have velocities of opposite sign. Velocities of gas molecules are positive and negative by assuming that all particles are moving equally in different direction. By squaring first, give all positive velocity, and taking the root of the square of the average velocity will give the average speed without direction. The root means square speed. Vrms is the measure of the speed of molecule in a gas, defined as the square root of the average velocity square of the molecule in a gas. Vrms is equals to square root V1 square plus V2 square plus V3 square plus Vn square over the square root of average speed. To compute the RMS speed, we square each molecular speed, add and divide by the number of molecules and take the square root. Here is the calculation of the root mean square speed. According to the kinetic theory of gases, gas pressure is the result of the collision of large number of molecules on the wall of the container. As gas molecules collide with the walls of its container, it will change direction. When this happens, the particles exert force on the wall of the container. By referring pressure P equals to F over A, the force exerted over a unit area by all gas molecules as they hitting the walls of the container around them is pressure. Pressure can relate to the root mean square speed of the gas. PV equals to 1 over 3 mass times number of molecules times Vrms squared. By rearrange the equation, and we can get P equals to 1 over 3 mn Vrms square over volume. And from density is equal to the mass times number of molecules over the volume. Therefore, we will have P equals to 1 over 3 rho Vrms square. we obtain an important result that relates the macroscopic quantity, which is pressure, to a microscopic quantity, which is root mean squares molecular speed. Thus, we have established a key link between the molecular world and the large-scale world. From the ideal gas equation, PV equals to nKT, we compare with PV equals to 1 over 3 mn Vrms square. nKT is equals to 1 over 3 mn Vrms square. So we substitute, we get 3 kT over m equals to Vrms square. And after that, after we rearrange and we simplify, we can get Vrms equals to square root 3 kT over m. We also can write as Vrms equals to square root 3 RT over m. M is the molar mass. Okay, here is the symbol used in this in the equation. M is the mass of molecule in kilogram. Big M is for molar mass of the gas in kilogram per mole. T is absolute temperature in Kelvin. K is the Boltzmann constant, and R is the molar gas constant. Lastly, this will indicate that the root mean square speed, Vrms, is directly proportional to the square root T and inversely proportional to square root molar mass. RMS speed of the gas will increase with the increasing temperature, and at a given temperature, lighter molecules move faster on average than heavier ones. On average, the nitrogen molecules with the molar mass 28 gram per mole in the air around us are moving faster than the oxygen molecules with the molar mass 32 gram per mole. Hydrogen molecules with molar mass equals to 2 gram per mole are fastest of all.